Hi. Now we'll see about the next discussion in our video lectures, which is about a rotating magnetic field. So in the last lecture which I have taken on induction motor principle, there was a discussion, there was a term called rotating magnetic field. We even have seen that whenever a three-phase balanced supply is given to three-phase distributed winding, then the three-phase distributed winding will produce some flux, and by its virtue it's a rotating flux. Now we're going to see about how a three-phase flux can result into a rotating flux, or in fact how a flux, a resultant flux of three-phase flux components would rotate in a induction motor. Okay, this is a beautiful concept which you will not find in many of the books too in a clear way. Maybe they'll explain with the sense of the waveforms, or in fact with a help of some vector diagrams, but I would like to explain you in a detailed sense that exactly how the magnet moves. Physically you can see that the movement of magnet, movement of the total magnetic field on the stator. Okay, shall we go on? Fine. Yeah, as we see that there is a stator, rotor with windings, and stator winding has got three-phase distributed windings, or three-phase distributed windings, and they are given with a three-phase supply. So what happens whenever you provide a three-phase balanced supply to three-phase distributed winding? As we have just now learned that we'll have three-phase fluxes phi A at an angle 0 degrees, phi B, phi C, and the resultant will be phi R, which will rotate in the air gap. So that's why this is called RMF. What is RMF? Rotating magnetic field. That's okay, that's fine. Now we're going to evaluate this reason, that how it is going to rotate. Fine. So let us start the understanding now like this. Okay. So let me first take the three-phase waveforms here. This is my three-phase waveforms. Let's say I will take my VA. You have to, I think you would have seen, had this idea about how to draw three-phase waveforms. Let's say this is VA. Okay, or I'll take this as IA. Okay, IA, the current which is flowing in the phase A windings. Okay, and next IB. What is IB? So the easier way of drawing it is, I'll take the peak points. This is 90 degrees, and this is my 270 degrees. So minus 30 will be 60, plus 30 will be 120. Okay, minus 30 will be 240, plus 30 will be 300. So according to this, I'll draw now. See, phase B will start at 120. So after 90, so it will extend until after this one, right? So I'll take this as a waveform, certainly maybe this. Okay, this is how my phase B comes, and then this is 120 degrees, so 60 degrees I should take this way. Fine. It's maybe the angle measures may not be exactly correct, but still I'll try to make it. Okay. Now you see, this is my IB. Okay. Next what? IC. So IC starts at an angle 240, right? 240. So yeah. So here I'll start from here, so it rises from there, and the remaining portion it just and then let me take the negative direction of it. So 270, this minus 30, so 90 minus 36. So these two will be, I'll be joining these two. So this is how I make a little easier understanding, my own understanding of drawing it. Even my professor has told me in a different way. It was too quick than this one. So anyways. Fine, and now this is my IC. That's okay. Okay, now how to realize the facts that the rotating magnetic field is really rotating You know, it's not the winding which is rotating, it's not the physical winding which is rotating, it is the flux which is produced in the winding rotates. We'll see that now how. Okay, now you see this is your 0 degrees. Okay, yeah, at maybe this is your, you know, omega t is equals to, let me take about yeah, 0 degrees. Okay, at what is that? Yeah, so not at 0 degrees, let's take at 30 degrees, right? 30 degrees. Okay, if I take omega t is equals to 30 degrees, then what happens is at this particular 30 degrees point, okay, 30 degrees point, you have phase A, IA positive, okay, and IB or IC, okay, IC positive, okay, and then IB, yes, it is now, what is it? Negative. Okay, so what is it, my dear? At this instant of time, if you see at 30 degrees, you are finding that IA is having a positive value and IC has got a positive value, but what about IB? It is negative. Okay, now you see, as per the Amperes right hand thumb rule, you know, thumb rule of Amperes, if the current direction is maybe, you know, positive or negative, whatever it is, or if the current direction is in the direction of thumb, you'll have the direction of flux in the direction of fingers, right? That's the Amperes thumb rule. Now you see, I would take my assumption that if IA is positive, I assume that the current is going in. The current is going in. Okay, the current is going in. Right? Right? If the current is going in, I mean the current is going in here. The current is going in. Okay, and what about IC? Here also it is positive. Okay, so which means in this particular winding, the current is going again inwards. Is that okay? So here what? IC is also going inwards. And what about IB? The current is negative. The current is negative, which means the current is now coming out. Coming out. Or if you want, you can indicate this as the current is going in maybe with a dot. The current going out maybe with a star. Okay. So now let me, these two are related. Okay. Okay. Let me indicate that here. The current is going in here, right? So if the current is going in into A, it goes all through the length of the conductor A and then comes out from here. So what I should take here, it is coming out, right? It is coming out. Right? Maybe I'll take it as a star for a clear understanding. Okay. Here maybe I'll take a dot. So the current is going in and the current is coming out. So very simple. The notation is very simple. If the current is going in, you indicate with dot, coming out, cross. So what is happening here? What about IB? IB means this conductor, okay? Okay, B phase, right? Here the current is going, coming out, negative, right? So coming out. If it is coming out, what I should make there? I'll just draw a little bigger one. Okay, so it is a star. Am I right? It's a cross. So, and if the current is coming out here, definitely the current would have entered at B dash because this is a pair, right? It's a coil. So the current has entered here. So I'll indicate this with dot. Is it making sense, my dear? Is it making sense? Okay. So the current is coming out here, which means the current has got into this B dash and coming out of B. This is how I can take this understanding. Fine. That's okay. And now what about the conductor, the current IC, the current IC. The current IC is flowing into this phase C conductors. Okay, so as I said in the discussion, like this conductor A will have IA, and B dash will have IB current, C and C dash will have IC current. Okay, maybe I can take more conductors also here, no issues. Phase A has got maybe can have maybe 50 conductors, but all of them have got the current direction inwards, and here all of them current direction outwards. Okay, all of them. Fine. Maybe here also you can take more conductors coming out and here going in. Are you understanding, my dear? Hope you are with me. Fine. And what about IC? Yes, IC, as I said earlier. Yeah, IC is about, what is IC? Yeah, IC is also positive. So here the current is going in, right? Going in. The current is going in. And here the current is coming out. So let me indicate that, a bigger one. Coming out. I have taken only one. If you want, you can take more, maybe 3. So the current is going in all these 3 because these are all the phase C conductors. And here the current is coming out. That's fine. That's okay, right? Fine. Now see, as per the right hand thumb rule of Amperes, if the current is going in or out, which is indicated with thumb direction, okay, if the current direction is denoted with thumb, then the flux that is produced in the conductor is indicated with the curled fingers. Hope you are with me, right? So if the current is, let's say for this one, yes, the current is going in, right? The current is going in. If the current is going in, then the flux direction will be, the current is going in, the flux direction will be in the direction of curled fingers, which means the flux will be this side, right? Yes, hope you got me. See, the current is, the flux is this way. It runs, it revolves. What about A dash? The current is coming out. If the current comes out, then the flux direction is in the direction of fingers, right? So if the current is coming out this way, the flux will be directed in the direction of curled fingers, something like this. Are you with me, my dear? Okay, fine. Similarly, for B, the current is coming out. The current is coming out, yes or not? So the flux direction will be in the direction of fingers. B dash, the current is going in. The current is going in, right? So you will have this direction flux. So you will have the flux direction this way. Is that okay? What about C? Positive current. The current is going in here. Means you will have this direction of flux. And here the current is coming out. So you'll have which direction of flux? Yes or not? Coming out. So this way. So its direction is this. Okay, my dear. See, what about the current directions in all the sects, in all the different, set of conductors? Phase A, the current, phase A current are the windings or the conductors which are concerned to phase A, okay, have got the current direction this way. The conductors, A dash conductors, the counterpart of phase A, the flux direction is this way, right? So this is how all the different conductors, different set of conductors have got different direction. Now can you observe the commonality here? See here now. Fine. Yeah, the current direction in A is this way, right? And the current direction in B dash is this way. And the current direction in C is this way, right? Are you observing? All the conductors, A, B dash and C. All these conductors have got a similar direction for the flux. Similar direction for the flux because the current is similar to them. Here the currents are going in, right? So the flux will be in the same direction. So if you can see, the current here is clockwise, here is also clockwise, here is also along the clock. Along the clock. So if I can, and the other side, A dash, the current is coming out. B, the current is coming out. C dash, the current is coming out. So here, if you can see, these 3 different set of conductors will have a similar direction for the current. Similar direction for the current as well the flux. Okay, so if you can see now, the flux is moving this way, right? And here also it is anti-clockwise, anti-clockwise, anti-clockwise. Now let me make it a concluding remarks now. Okay, see here now. All these 3 will have similar direction of flux. Let's say all the flux will move like this. Okay. Yes. Clockwise. Clockwise. Is it making sense, my dear? And what is happening here? All the different three different sects here are having anti-clockwise direction for the flux. So here I can make the net resultant flux. Net resultant flux moving this way, right? Okay, are you understanding now? The flux is coming out from this edge and going into this. Are you getting my idea? The current is, the flux is recepting at this end, and the flux is ejecting from this end. Ejecting, ejecting. Right, my dear? Fine. Eject. So, from which end the flux ejects if you take any magnet? Simple. North pole. And from which end the flux recepts? South pole. So this is a magnet. This is a magnet, which means it is not a permanent magnet. In fact, it's a electromagnet. In any motor, wherever there is a word called artificial magnet is seen there, this is how it works. Okay. So now at omega is equals to 30, this is the magnet. This is the resemblance or a kind of understanding about how the magnet will appear, will work, will have its resemblance in the windings. Okay, right? How many poles are there now? Only two, north and south. Okay, 120F by P. If you take NS equation, 120F by PP is number of poles, right? So how many poles you have? Two. In the last discussion, I mentioned that here, there are many conductors, but number of conductors doesn't. It is not equal to the number of poles. Number of poles. How many conductors are there here? There are more number of conductors, but still the number of poles are only two. So it depends on that. Okay, based on the winding, the number of poles will change. Sometimes we'll have 4, sometimes you'll have 6. Maximum 6 you'll have, because as you increase the number of poles, you'll have the speed ns lesser and lesser. Okay. Fine. So this is the magnet which is seen. Discussion is not finished yet. Okay. So let me take another few minutes. If I take at let's say 90 degrees. If I take at 90 degrees, let's say at this particular angle, 90 degrees. Okay. At this angle, then what is there? IA is positive. And what about IB? IB and IC both are? Yes, my dear. IB and IC both are negative. Okay, fine. Right, okay. If IA is positive, the current is inverts into A dash. The current is, see, as I said here, the current will be inwards and negative current is taken as the current outwards, right? If the current is positive, we'll consider the direction in the conductor for the current is inwards. If it is negative current, the current direction through the conductor will be outwards. Okay, so what is this now? IA is positive. So IA positive means A will have inwards that direction and A dash will have outwards. So it is as it is. There is no change here. Here IA positive, here also IA positive. Okay, let me tell you about IB. IB is negative, was negative here at 30 degrees, and here also IB is negative. So IB, where is IB here, right? So this also, the flux direction will not change. So here it is negative, right? So you'll have coming out direction here and going in direction here. Same like the previous one, because this and this are going to be same. So IA positive, IB negative, IA positive, IB negative. Okay, which means this IA, phase A conductors and phase B conductors will not have any change in the current direction as well as in the flux direction, which means they are unchanged. I'm not going to change anything there. But what is changed here? At omega t is equals to 30, you would see that IC is positive, but here IC is negative. So when you see, I mean, the current direction through the phase C is reversed, which means what? The conductors which are carrying the current IC will have a current reversal through them. Very simple, right? So earlier at omega t is equals to 30, the conductors which are of phase C were having a positive current, and now they're going to have a negative current. Okay, fine. So phase C conductors means C and C dash. Now come to this now, okay? C and C dash. So what is C now? C is negative. So which means here the current direction C, right? The current direction will be here. What direction will have? Current direction. So negative, right? So we'll have current is coming out. Current is coming out. Fine, my dear. So if the current is coming out, what about the flux? In the direction of fingers, right? Coming out current, right? So it will be in this direction. Okay. And now what about C dash? Here the current is going in, right? If it is coming out here, which means the current would have entered there, right? The other side, counterpart. So I will take this C dash. Here the current is entering. Current is entering, right, my dear? Fine. Okay. When the current is entering here, what about the flux direction? What about the flux direction? Okay, the direction of fingers. So cross according to Amperes thumb rule. Fine. Okay, that's good. Let me remove the impressions of the discussion on at omega t is equals to 30 degrees, okay, because it's going to change now. But remember this axis, what is this axis? It is a magnet. It is the axis of the magnet, I mean electromagnet, that is seen at omega t is equals to 30. Now because of the polarities of current is changed, you will have a difference. I mean we'll have a different axis for the magnet, which we're going to see now. See here what's going to happen. See this conductors A, B dash and C dash, okay? A, B dash and C dash. These three conductors have got a similar direction of flux. Am I right, my dear? See here, clockwise, clockwise and clockwise. Then what will happen? Tell me. So here, between this, only this, you will have a resultant magnetism between them, which means here the flux direction will be like this. See, the flux is moving, right? Alright, very nice, fine. So this is how the flux direction here is clockwise, and here is clockwise. Thereby the net of three different sets of conductors have got a resultant flux moving around like this in the direction of clockwise direction. Okay, right? Now you see, what about the other set of conductors? C, A dash and B. C, A dash and B. See there, the current direction is anti-clockwise. Am I right? So here what will happen? The net resultant flux will be anti-clockwise. Okay? Anti-clockwise, right? So this is how you have it. Fine. So what is this now? Anti-clockwise means it's going like this, right? So fine, that's okay, that's good. Fine. So see this one, these three have got resultant flux, and these three have got resultant flux. So what is happening here? Can you observe just for a minute? Okay, so here the flux is coming out, so it's called now my north pole, and here the flux is recepting, coming in, south pole. What is the axis of the field? So field axis is this right now. Okay, so what happened? What happened, my dear? This was the axis when omega t is equals to 30. This is the axis when omega t is equals to 90. So there is a angular shift of 60 degrees, if you can see exactly. Okay, if you can measure and make some analysis, you'll have 60 degrees shift of the magnetic field, neutral axis. That's fine. See what happened here. So when you had at omega t is equals to 30 degrees, your magnet was having an axis like this in this fashion. See this one. And now as you go along with the time, as the time is proceeding, maybe at omega t is equals to 90 degrees. So omega t is equals to 90 degrees means how much time, my dear? After 5 millisecond. I mean to say this is 1.667 millisecond and this is 5 millisecond. If you can convert 360 degrees into 20 millisecond, and then 90 degrees is 5 millisecond, 30 degrees is 1.66 milliseconds. So this is 1.66 milliseconds. So after certain milliseconds, let's say at 5 millisecond, okay, you would find the magnet which was seen this way is shifted. So are you understanding now? So what's happening? You can imagine now what happens if I take at omega t is equals to 150 even after 60 degrees. Even after 60 means 3.33 millisecond. After 3.33 millisecond, this magnet will move a little down by another 60 degrees like this. Maybe here. Again after 60 degrees, maybe at 210 degrees. 210 degrees means around 181, I mean about 11.667 milliseconds. At 11.667 milliseconds, you will find it will be maybe here. So what's happening here? The magnetic neutral axis is moving. I mean to say the magnet is moving. The magnet is moving. That's how I can say the resultant flux phi r is not static, is not stationary at one angle. It is moving 0, 60, 90 and then 180. It moves, it keeps moving. The resultant flux moves. It doesn't stay at one particular angle. Are you understanding? So when if I take at 0 degrees, the magnetic axis, the magnet would could have been yes here, n here. If because I have taken at 30 degrees, yes is here, n is here. Because I have taken, I have evaluated for 90 degrees, I could find that the magnet is shifted. Axis is shifted to this side. If I take 150, this magnet shifts this side. Are you understanding? So this may be 0 degrees, 30 degrees, 90 degrees, and then this would be your 150 degrees. So it keeps moving. Okay, so this is how you would find the rotating magnetic field is not is rotating. How is it rotating? This is how we can evaluate the fact with the help of these three-phase waveforms at two different instants. So two different instants will tell us that it is moving. If you want, if you are not satisfied with this, you can go ahead for every 60 degrees. You can take that current directions, indicate this, and then check. You will find the magnet, the field, the magnet phi r, the resultant flux would keep moving with respect to the the time that you take on the x-axis at different angles. This is how it is. Have a nice time. Thank you.